I do want to point out that we didn't have to use Gauss's law. That if I am outside of something of spherical symmetry, I could just treat it as a point particle. So when I am here, well, we did that for here. I could have just used the electric field formula. The electric field is equal to KQ over R squared, R hat. And you would have gotten to the exact same place. When I'm here, the total charge is 8. And because of spherical symmetry, you can treat it as 8 coulomb charge smack dab in the middle. And here, 6 coulombs smack dab in the middle. Now, if you're looking at this equation and that equation and going, wait a second, they don't look the same. Well, actually 1 over 4 pi times epsilon naught is the same as K. It's Coulomb's constant, so. However, Gauss's law does have a use, which we're about to demonstrate. Are there questions before I just dazzle you with some derivations? Erica's ready to go. Let's do it. What I'm going to do is I'm going to have an infinite line of charge here. Now, if not infinite, an incredibly long line of charge, such that I'm not really going to get too far off of it. So I'm now this distance right here. Why don't we go something clever like a distance r? This has a uniform line of charge, and we are going to label that lambda. It is the charge per unit length. It's the linear charge density. Linear charge density. And what I want to know is, what is the electric field at distance r away? Now, if we were doing it using Coulomb's law, then we would have to figure out, well, I've got a small little bit of charge right here. It creates an electric field going in that direction. And then, but the strength of that electric field is going to change as I go along here. It involves calculus. In as much as I'm sure all of you deep down inside, while you're dancing the jig of joy, are going, wow, I'd really love to see this done with calculus. I'm going to suppress that. I've had a lot of practice as a father to suppress ambition and wants. So, no, we're not doing calculus. But we will use Gauss's law. So what I'm going to do is, at first, before I can use Gauss's law, I need to create a surface. I need to create a virtual surface, which I will do. And so, basically, I'm creating a cylinder. I'm creating a cylinder that is of length, let's be clever, L. Now I know Gauss's law says that the electric flux, in other words, the sum of all the E dot A's, is going to be equal to the charge enclosed over epsilon sub naught. So first thing, let's figure out what the charge enclosed is. I know this is length L. I know that the charge is lambda, that the charge density is lambda. In other words, it is some charge per unit length. Well, I can figure out the charge that's enclosed just by multiplying both sides by the length. So my charge enclosed is just going to be lambda times L. If you wanted numbers, this would be something like 3 microcoulombs per meter. Then I just multiply times however many meters I got. Now my electric field, I know that my electric field has to be going away from the line. my electric field has to be going in that direction, all the way around, but it has to be going directly away. And how do I know that? Well, I know that at this point right here, from here, I have an electric field going in that direction. But for every point over here, I've got one over here that's going in that direction, and all of the horizontal components would cancel. The only thing I'm going to be left with are components that are pointing away from the line. And we will exploit that now. So my electric field is going in this direction. Well, there's one little symbol I'm going to add here. I'm going to put a little circle there. And I should have done that. It seems like, yeah, I should have done that over here too. And that indicates the fact that it is a closed surface. Without that, it might, mathematically it implies that it doesn't have to be a closed surface, but for Gauss's law, it does have to be a closed surface. So we're going to basically do this for my cylinder. I got two end caps and I got the main body. So this is going to be E dot A for the left cap, plus E dot A for the right cap, plus E dot A for the, let's call it the barrel. And that's going to be equal to my enclosed charge divided by this constant. Now, you might be looking at that and going, wait a second, that doesn't really help me. Well, yes it does. Because two of those are equal to 0. The question is, which two are equal to 0 and why? Well, considering I have left cap, right cap, barrel, if you had to pick out two that were going to be equal to 0, which ones would they be?
The caps.
Okay, so the caps are equal to 0. Now, the real question, why? Why is the electric flux through the end caps equal to 0? My thought that I'd be having the dance of joy inside seems to be fading. It's not gone yet, though. What is the direction of the area vector in general? If I got a surface, what's the direction of the area vector?
Perpendicular to the surface.
Yes. So if I'm on the end cap, what's the direction of the area vector here?
Parallel to the surface. Wait.
That way.
That's up the, yeah, that way.
Following the line.
So there's my area vector. I know my electric field is going that way.
So they're gonna cancel out?
Not really the right wording. Apparently,
It's a dot product.
what?
It's a dot product. And
Yes.
not a cross product.
If you're doing a dot product, what's going to be if two vectors have a dot product equal to 0, what can you tell me about the vectors?
They're perpendicular.
Yes. Dot products multiply parallel components. If they are perpendicular, the dot product is 0. That is 0 and that is 0 because the electric field is perpendicular to the area. It's not perpendicular to the barrel. They are, as a matter of fact, exactly in the same direction. The electric field and the area vector anywhere on this barrel are the same. And if you're having trouble, I know my drawings are just beyond comparison. But I have a barrel right here. My area vector is always perpendicular to the surface. My electric field, because I got my line running through like that, my electric field is pointing outwards in the exact same direction. Because of symmetry, it is perpendicular to the surface. So that is just my electric field magnitude times the area of the barrel. And what is the surface area of the barrel? Surface area of a cylinder, the side of a cylinder. If I took a cylinder like this and I cut it, and then I open it up, what would it look like?
A rectangle.
Okay, area of a rectangle.
Length times height.
Okay, so all I need to do is figure out how far it is around here, because that would be the length. And then I need to figure out that distance. Well, that distance around there is just the circumference. And then that's, in this case, L. And that will not work over here. So I have EA is equal to lambda L over epsilon sub naught. E is equal to lambda L over A epsilon sub naught. And that's going to be equal to lambda L over, all right, so A, the area of the side of a cylinder. What's the circumference formula? There are two circle formulas. It's going to be one of those. Matter of fact, since it is a length, it's going to be the thing with only one dimension.
2 pi radius.
What'd you say?
2 pi radius.
Yeah, 2 pi r. 2 pi r times L. Epsilon sub naught. Hey, the L's cancel out. So that was sort of arbitrary, the fact that I made it some length L there. And what I'm left with is that the magnitude of my electric field, it's going straight away from the wire, is equal to lambda over 2 pi r epsilon sub naught. Traditionally, that r is stuck out front, because that's just some constant related to the problem. We have the charge density, we have, and then the denominator here are just all constants. But the farther I would get away from the line, the weaker the electric field. That makes sense. Perhaps another way of thinking about the electric flux. Suppose I have arrows shooting from that wall to that wall. And I put a piece of paper here. The flux is a measure of basically how many arrows are going to penetrate this. As I start to, so the area vector here is perpendicular to the paper. In other words, it's going to be parallel or anti-parallel to the arrows. So I'm going to get most penetration this way. And then as I tilt this, there's less and less surface that's exposed to the arrows until I'm like this. The electric flux is 0. We're not doing a Robin Hood split in the side thing. And speaking of which, why does Robin Hood win? Because he hit the exact same spot as the other guy when the whole splitting the arrow thing. They hit the exact same spot. If the other guy had gone second, he would have split the arrow. Anyway, so that would be electric flux of 0 because you can't penetrate a one-dimensional surface like that. So maximum flux minimum flux. We can put it in terms of, I'm gonna leave it in epsilon. There's obviously a relationship between epsilon sub naught and Coulomb's constant, but why? Questions? All right, I can sense the excitement. We've done sphere. We've done infinite line. Let's do infinite plane now. Yeah, that's right. This is the day we're doing infinite plane. Wait, cycling. Jaunty tilt view. Front view. Except it goes on forever. It's an infinite plane. And I want to figure out what is the electric field at distance r away. No, actually, I want to use r for something else. We'll make it a distance L away. So I want to figure out what is it, if that distance there is L, what is the electric field at this point? And it's not on the surface, it's in front of the surface. We will, of course, use Gauss's law. But if I'm using Gauss's law, I need to create a Gaussian surface. So what I'm going to do is I'm going to use the cylinder again, except this time the end cap is going to be at the point that I want. So I'm going to have a cylinder acting like that. And that point of view. Let's see what I have. Anybody see a slinky in here? Ooh, there we go. So as I have my surface here, and basically I'm creating a Gaussian surface like that. Well, I know Gauss's law. At this point, we all know Gauss's law. I know that the electric flux through that Gaussian surface is going to be equal to the enclosed charge over epsilon sub naught. So this is going to be equal to the sum around the closed surface of E dot A. Let's see, we can do better than that because this has to have a charge on it. If it doesn't have a charge, there's no electric field. So we'll give it a uniform surface charge density. Sigma. And sigma would just be the charge divided by the area. So whatever area I pick, I'm gonna have some charge. It's going to, if the area doubles, the charge doubles, etc. Since I have a cylinder here, so this is going to be equal to sigma times A over over epsilon sigma. But recognize what this A here is. This is the area that, where there's a charge. It is that area right there. That is the charge that is enclosed by my Gaussian surface. It is a cylinder. I do need to give at least some dimension of distance here, so why don't we just cleverly call that little r. So little r is the radius of the cylinder. All right. Putting this into pieces here, we have, so that would be the electric field through, we'll call the left cap, I'll just abbreviate it to LC. Through the left cap times A of the left cap, plus the electric field of the right cap times the area of the right cap, plus the electric field on the barrel times the area of, dot product with the area of the barrel. It's going to be equal to, well, sigma times this area here that I've hashed in black, pi little r squared over epsilon sigma. Dramatic pause for people to catch up in writing and to ask questions. All right, are any of those dot products equal to 0? What's your gut feeling tell you?
Yes.
Okay, your gut feeling is correct.
Yeah.
Which one is equal to 0?
Barrel.